to CO2 equivalent by multiplying the molecular weight. So you can get to, here's the weight of the forest, this is the approximate amount of CO2, or the equivalent amount. So this is just what it looks like. If you're using synthetic aperture radar, it can get you kind of some forest structure because you're shooting microwaves at it and you're getting certain reflectance based upon the forest structure. L-band will penetrate more into there. C-band will get some volume scattering off of trees, for example. So one of the biggest changes in this space lately, certainly in terms of what's available in Google Earth Engine, is NASA's Global Ecosystem Dynamics Investigation, or GEDI. This is a really nice animation from their website, so I cited it from there. So we're using this a lot here. So it's essentially on the International Space Station, shooting LiDAR down at the ground and then getting attributes, as you see there, from the forest canopy. So you're getting a 25-meter footprint and you're having a bunch of returns there. So again, this is all their stuff here. I'm just showing it because we use it quite a bit in our models, essentially. So it's pretty much global. It's not in polar areas, so in northern areas of Canada, it's not. But it's pretty much everywhere, and it's good training data for biomass, forest carbon. So essentially, this is kind of like a scientific exercise. So you ask a question at the start. Can we use newly ingested into Earth Engine GEDI L4A biomass? So that's what the training data is there. If you saw the animation before, that's what you're using to predict forest carbon. So we're going for continental scales. So predicting it over all tropical regions in Africa, or predicting it over all of Indonesia and Southeast Asia. And then we're also using this for some commodities. So that's probably where my company is very interested in this. Can we use this technology to assess carbon stored in shade trees of cocoa and coffee crops? A lot of tropical areas, certainly there's a lot of cocoa and coffee crops there, and you can store a lot of carbon in the shade trees, as those are both shade crops. So just for example here, I believe this is cocoa, or it could be coffee. Anyway, one grown full sun, the other grown with lots of shade trees. So obviously the one on the right stores quite a bit more carbon with shade trees above there, and we have the crop below. So how do we do this? Into the methods, we essentially have right now 3 key areas for forest carbon biomass prediction. So these are very large areas. They're covering tropical areas of South America, Africa, and Southeast Asia. This is essentially the areas we're going to train our models on. All right, so getting into when we're starting to work in Earth Engine. So first, we're going to get our GEDI L4A. So these are above ground biomass density derived from the GEDI L2A waveform. So these are 25-meter footprints. We'll hopefully see what this looks like soon. So processing steps, there's a lot of key ones. This is from various literature online. So you got to do quality flag, degrade flag, get unreliable points out, high slope footprints. So essentially, if you take a screenshot in Earth Engine, that's what the GEDI data looks like if you were to pull it up in the code editor. I just put a little picture here. Like, I walk these forests almost every day in Canada. They're fairly large conifer forests. So that's what they look like on the ground. And you have these little tracks along here of 25-meter footprints that will get you above ground biomass density. So that's in tons per hectare. So fairly tall forests here. So you have some of the taller forests that are upwards of 600 tons per hectare of biomass. And then you can see the lower values in areas like swamps or rocky areas right here. But that's what it looks like. You can see that this isn't like wall-to-wall sampling, so we can use this as training data in our models, essentially. So yeah, a little bit of how we process the satellite data. There's a lot online about how to process proper data in Earth Engine, Sentinel-1 and 2. Sentinel-1 and 2 might not actually be the best sensor for biomass prediction, but they are open access. They're available globally at 10 and 20 meter resolution, and they're processed rapidly in Earth Engine. So that's why if we're wanting to do a continental scale analysis, these are probably the best options. We also have ALOS pulsar data in here. That's a little more suited for it. So what we're doing to Sentinel-1, terrain correction, speckle filtering, orbit filtering. At the end of all this, you take the mean of the image stack, and then you're getting outputs of VV polarization, BH, and some polarization indices. So Sentinel-2, we're taking all images in 2020. Google released a new cloud and shadow masking. It's essentially called Cloud Score Plus. So it's really valuable for getting good cloud-free images, especially in areas like Western Africa where there is lots of clouds. And then here we're going to take the mean of, or the median of the image stack. So essentially the middle pixel and all that. We then output a bunch of vegetation indices like NDVI and all 10 and 20 meter bands. Finally, not to go on this too much, but ALOS pulsar. So this is L-band synthetic aperture radar, conversion to decibels and mean image stack. And again, outputs similar to Sentinel-1, but this is in the HH-HV polarizations. And then, yeah, those are screenshots, what it looks like in Earth Engine. So I believe this is close to Nairobi. So the Sentinel-2 NDVI and the ALOS pulsar. This is one of the more important indices for biomass prediction. The higher backscatter usually means higher biomass. Oops, that's not supposed to come up there. So JEDI L4A, so how are we going to train these models? We can't compare directly the 25 meter footprint to the Sentinel-1 and Sentinel-2 pixels. The geolocation doesn't match up, and there's a lot of noise. So you essentially need to aggregate this JEDI data and the Sentinel and ALOS data into segments. So you can kind of see the Earth Engine code here. So we're kind of spatially getting spatial statistics from these segments. So we're getting the mean, standard deviation, and the second and 98th percentile, according to this Earth Engine code here. So we're doing all these spatial reducers here, and then putting that into a big training stack in Earth Engine. So we end up having around 100 input variables to these models. We're going to filter that down later. But with all these spatial statistics and all these 3 input Earth observation platforms. All right, so machine learning, how are we doing this? So we're using the mean above ground biomass density as before. So usually that ranges from 0 to 1,000 tons per hectare in some of the bigger forests. And then we're using the out of the box Earth Engine gradient tree boost. You can see here, that works pretty well. So it's modeling in tons per hectare. And then generally we're only keeping the important bands for prediction. So this tends to be ALOS pulsar, L-band was very good, and the red edge Sentinel-2 bands and indices based upon that. So our model results are here. So if we take our predicted above ground biomass and then our validation from JEDI, what it's telling us on the ground from those models, this is our correlation. So we have a square root here. This was to kind of help fit the model, but our Africa model ended up being the best with a R squared of 0.86 and a root mean squared error of 17%. So compared to other ones, we're not expecting an amazing fit here. There's a lot of sources of error, but specifically the Africa tropical model worked fairly well. And then here's the Asia model. We also have a South American model. That one I think is very similar to the Asian model. So we see a decent fit here, meaning that, yeah, our results are somewhat accurate. Of course, they're not going to be perfect, but generally it's a good estimate of above ground biomass. So I tried out some predictions just to show everyone. So yeah, Nicholas pointed me to an area in Kenya that could possibly work. So I ran the model here for the Mau Forest area. You can kind of see the results and the predictions. So our Africa results were actually very good. So I was eager to try them out. Predicting, yeah, fairly high biomass here. I believe this is a large area, but I kind of cut it off. If you're looking to use this at all, for any research there, it is an Earth Engine asset that's open under my account. So feel free to use this data. Yeah, it is open and on there. I hope to produce more, but yeah, for certain areas, like I've done it around where I live, and I'll show that in the next slide. So it's essentially, yeah, predicted at 20-meter resolution for this area. So using all those models, it's put into segments essentially. So about 1 hectare segments, which I'll show you in the next slide. So yeah, similarly, this is Vancouver Island in Canada, where I live. So I wanted to run it for this area as well. So this area had a different model, of course, than Africa. It's for more northern temperate ecosystems. I'll just pull up the results here, just so everyone can look at them. So yeah, you can feel free to access this app as well. It actually hosts the results. So as you can see, when we zoom in a little more, yeah, it's divided kind of into these segments. Here, that area has snow in it. You can see the segments, they're 20 or 10-meter resolution, but divided into homogeneous segments. So it's kind of easier for the algorithm to predict, given you can give it spatial statistics to predict off of. So you can see this is a lot of harvest area right here, higher biomass here, and then when there's been recent harvest of the forest, of course, lower biomass. Oops. So yeah, here, feel free to access this Earth Engine asset and use it. Just cite this presentation if you're using it for anything. And then this data here, there's a Earth Engine app. And then finally, just go over this. So this is also being used for coffee and cocoa crops to measure carbon storage, as I mentioned before. So these models also work well, especially when there's a higher proportion of shade trees. If it's a full sun-grown crop, JEDI methods don't really work that well. And then essentially this can be returned into a reporting tool for getting shade tree carbon or CO2 equivalent from predictions. So you can essentially click on a crop if you know where it is, say, hey, this coffee crop holds this much carbon in the shade trees. So yeah, this is pretty much a need for a lot of these coffee suppliers, especially with new regulations, to know how much carbon is stored in their shade trees and their crops. And yeah, it's fairly similar methods, but essentially we're trying to train on more areas over cocoa and coffee crops, because they're kind of a different ecosystem. They're not this primary forest, they're shade trees with coffee and cocoa below. So essentially the take-home messages, so large-scale biomass density estimation can be done at continental scales in Earth Engine. Earth Engine provides that platform to do it really over large areas and fairly rapidly. But we have to note this is not really an exact predictor. So the JEDI data we're using is modeled. It's not on the ground measured. And input Earth observation data just naturally has quite a bit of noise. And then to improve this, really the aggregation of the JEDI points into segments really has the biggest effect on model fit. And in the end, we would love validation from on-the-ground sources, not just JEDI data, to truly validate our model. So hey, we're saying this patch of forest has 500 tons per hectare. Ideally, you'd have someone on the ground measuring the diameter of the trees, the height, to actually get an estimate. Is that really what we're seeing on the ground? So yeah, it's only currently modeled on JEDI data. All right, that's pretty much it for me. Yeah, thanks a lot for the invite, Nicholas. Thanks for setting this up. Yeah, contact is there. So LinkedIn is a good one to contact on if you have any questions. And hopefully I'll be sharing more of this work. I know, yeah, we're hoping to publish and getting some Africa results out there shortly.
Okay, so thank you very much. Thank you very much. Evans. We do appreciate your presence and your presentation. At this time, I would want to welcome any question for Evans. So for the team, if you have any question, you can just ask him before the session ends. So welcome for any question, please. You can type on the chat or you can just open your mic and ask.
So I saw in the chat tutorial on this. Yeah, essentially, yeah, I could share a tutorial. So there's definitely some training ability or for this. Essentially, a lot of it could be, yeah, sharing of the code, open publishing of the code. I know that's easy in Earth Engine. You can just get the link for it. So yeah, we plan on definitely sharing some of the code for this, especially the processing of the satellite data. And then, yeah, in the end, we kind of want this to be a function you can kind of run and say, hey, I want to get above ground biomass for your study area.
Yes, Joseph.
Okay, thank you for the nice session, and I appreciate that. My question goes to the estimation of the carbon for the shade trees. How large should that area be for you to be able to estimate the carbon? Maybe should it be a large scale, or what's the amount of area which you can quantify to estimate that area? Because that is very important when you come to things like agroforest. Thank you.
Yeah, definitely. Good question. So essentially, we would want like the cocoa or coffee farm to be like half a hectare. If it's really small, yeah, we couldn't really get enough spatial information from satellites. But if it's like half a hectare or larger, generally using half a hectare to like 20 hectares. And then we can do this accurately on there. Because, yeah, essentially you want a few Sentinel 1 and 2 pixels in there to be able to do that. And generally, most farms are half a hectare, but I realize there's definitely some smaller ones.
Thank you for the response. And also maybe regarding that one, we'll be getting the carbon stored for the shade trees. And is it possible to be able to get the carbon stored in the crops themselves?
So that's a little harder because they're underneath the shade trees, right? So lately we've just been saying, hey, this coffee tree is what, 20 or 10 years old. So therefore it should have about this much carbon stored in it. If we're actually getting like penetration of the shade tree canopy, we can do that. So lately we've just been saying, yeah, this coffee plant is this year or this many years old, so therefore it should have about this much carbon. It's more of like a general estimation. But I think in the future, if you have radar that can kind of penetrate the canopy and get some reflection off the coffee and cocoa, I think it's possible to get the above ground biomass and carbon from that. But yeah, great question.
Okay, so for me, Evans, if I would also ask, is that the scalability capability of the system, like imagine now if you wanted to assess the carbon stock for a small scale farmer, how scalable, how flexible is the system to be able to monitor like one farmer who is next to another one, and the next farmer is probably has not planted the cocoa or the tree we are wanting to monitor. So that scalability aspects, like a small hectare, another one has a big one, those changes. Yeah.
Yeah, so that's essentially what we're working on a lot. Yeah, if you have a bunch of farms next to each other, I mean, different shade tree management practices, right? So
Yes.
we hope it's scalable to we can cover all of them if we're essentially training our model on all of those farms, right? We're like, hey, the Jedi has flown over. This is what it says about how much biomass is stored on that farm. We can hope to, scale it up so we can predict all there. So we can see each farm has different shade tree management practices. And then, it's good generally just to report that. You say, hey, my farm has much more shade trees there. It's storing much more carbon. Therefore, it's a much more sustainable sourcing of coffee and cocoa.
Yeah, I can see Joroge has posted a question here. It's a bit
Oh, yeah.
long.
So in lieu of the Jedi model, how can one work starting with raw data? The processing, machine learning model, automation, end goal to create a pipeline or similar data set input, automatically classifies the segment. So essentially with the raw data, I mean, that would be the satellite data, right? So that's really learning a lot about the best ways to process Sentinel-1. There is a package online. I could probably share that. It's a published package that Google did to turn Sentinel-1 into analysis-ready data. So that's a big one. And then, Google's Cloud Score Plus is a big one for Sentinel-2, just getting really good cloud-free images. So especially when you're working in tropical areas, that's some of the most important aspects of it. So hopefully that answered that part of the question. And then, automatically classifying the segments. So that's essentially putting your model in there and then pumping out results in Earth Engine. That's where Earth Engine's really good. You can get predictions over all of Africa, for example. And then best resolution for atmospheric carbon. Oh, atmospheric carbon. I mean, I think there's a lot of other products on there. They're not really great resolution because that changes a lot more. But I know there's a lot of products out there. I believe in the Earth Engine community catalog, there's some atmospheric carbon ones. As well as commercially available data, so I can get tree thickness. That's the estimation of the weight. So thickness, I mean, we're really measuring that indirectly. The best way to get tree thickness is, go in the field and measure the tree. But we're hoping, I mean, some of the SAR data, which kind of reflects off the trunk and reflects off there, is some indirect measure of tree thickness. It's usually tree height and density we're getting. So not true measures of biomass. It's kind of an indirect way of getting there. Yeah, great question.
Yes. I also do have a question.
Yep.
So mostly, I think I had worked with Get Data before, but majorly I saw you're predicting based on Sentinel-1 and 2. Is it possible to do the carry out prediction Landsat? Like, for example, let's say you want to just maybe have an overview. How does the carbon varying from maybe 2000 to maybe 2024 using Landsat images? Is it possible to do that?
Yeah, definitely. Yeah. So I think the model results will probably be worse with Landsat, but you can definitely do that. You could probably use the exact same methods and do it for way back. I mean, till 1984 if you really wanted to. But I mean, optical data isn't quite as good for above ground biomass because you're not really getting much penetration into the canopy. So that's why ALOS and Sentinel-1 are valuable. You can still definitely do it with optical. You'll probably just get worse model results for. So for example, there was 0.8 R squared, so you might work with 0.6 or 0.5. So essentially, less sure about your results, but Landsat you can definitely do it with. I've always wanted to try that and going back in time. Pretty much just haven't got around to it.
All right, so
okay.
Should there be any other question? Okay, so it seems like there are no more questions. So we would love to end our sessions at this time, and we appreciate very much, Evans, for your time, for sharing with us. It's really insightful session for us to learn. So
Can I ask something?
yes, please, Richard.
Yeah. I just wanted to ask, what software did he use to present? Because I don't think it was PowerPoint. I have a presentation coming up. I'm trying to understand what's best to present, like data and graphs and stuff. So what did he use to present? What was his?
I was on
PowerPoint?
I was on Google Slides.
Oh,
that was
okay.
what I was using. Yeah, it's just easier just to not have a local PowerPoint file. Just have it with my Gmail account, and I can pull it up wherever you can access that.
Oh, okay. So thanks.
And I see one more question in the chat.
Yeah, Hamad is here. Hamad is a PhD fellow, so
Okay. So yeah, how does Earth Engine overcome challenges of accurately mapping forest carbon levels, especially in dense and diverse forest regions? So yeah, that's essentially what I'm trying to answer and see if it does work. So for these tasks, it was 3 different forest regions on 3 different continents. It works differently for each one. These were all tropical regions. So yeah, this is where we're expecting lots of biomass and lots of forest carbon stored. So the hope is that it's kind of applicable over, hey, these kind of tropical regions in Africa, all are somewhat similar. That's, I'm sure, where you're getting a lot of air from. It's like, okay, this forest behaves very differently from this forest on the other side of Africa. So there's definitely some inherent air there. The hope is that we can say, hey, this is a tropical region of Africa. This is more of a savanna region. It can also work in Canada, in northern temperate areas, if you design your model for that specific region. So I don't know how big these regions should be. I know, for example, Canada should have its temperate rainforest be a region. Probably the Amazon in South America should be very similar, its own region. You could get smaller region, but that then takes more time. Obviously, you can't apply the Africa tropical model to Canada because those forests are very different. But yeah, you want kind of generalized regions, say, hey, this is tropical forest in South America. It should all kind of behave somewhat similarly. Obviously, there's tons of differences, but for modeling purposes, yeah, a somewhat generalized area.
I can see Joseph is having his hand on, please. Joseph.
Okay. Yeah, regarding the models, since they are basically created for specific, maybe forest, maybe let's say this model is for this temperate forest, and this one maybe is for the shade trees. Do we have the model maybe for the calculation of the above biomass, maybe for the plantations, maybe for the coffee plantations only, whereby we don't have the coffee shades?
Sorry, I didn't get all that question, I think. I heard the end part about the cocoa trees.
Okay. So basically it's regarding the fine-tuning the model to the purpose they are serving. Maybe they are serving the temperate forest, we have the model for them. Maybe we have the model for the rainforest, we have the model dealing with the rainforest. Then do we have the models maybe for the coffee plantations? Maybe we are dealing, maybe we want to estimate the biomass in the coffee plantations only. Well, maybe let's say we don't have the shade trees in that area.
Yeah, so essentially, yeah, separate models for cocoa and coffee plantations. A great idea as well. And when we don't have shade trees, that's where, I mean, I think the NASA scientists with JEDI advise JEDI is not very good at like very low biomass ecosystems. There'll be a lot of inherent air in there. It's more designed for tropical forests when you're having tall trees. So if it's just coffee and cocoa without shade trees, the JEDI data isn't that reliable there. Essentially, when I filter it, you remove a lot of those points. So that's why I think I had a note in there saying it doesn't really work well in full sun areas if it's just coffee and cocoa.
Okay, thank you.
Mr. Joroke is also requesting that you can
Oh,
check
yeah.
on the model part.
Okay, so repeat how the model varies with respect to climatic regions, miss down on it, which aspect change, when the regions vary. So yeah, I didn't really get into this too much. So the model varies with respect to regions in that we've just run it over 3 areas right now, so 3 of the tropical regions in the world over 3 continents. These essentially vary between their accuracy and the input JEDI data. So the input JEDI data also has accuracies for all these regions. I believe Africa had one of the better regions accuracy-wise. You can read the JEDI paper. That's online. That'll show you how the JEDI data varies between those regions. So essentially different kinds of forests, their models will be different and our models will be different as well. So we didn't really, I mean, the only other climatic region I tested was temperate regions in Canada. And those methods work just as well. It's just the trees are very different here. Mainly, yeah, conifer trees, similarly tall, different forest structure though. And it still works well, but that's because the JEDI models are essentially tuned to northern Canada as well. So hopefully that I wouldn't necessarily be the expert on that. I'd normally just read the paper produced by the JEDI team at NASA.
Okay, so thank you for that. I think okay. Joseph is also asking, kindly share the link for estimating the map forest. Okay.
Sure. Yeah, I think probably. I mean, if you follow on LinkedIn or if anyone's on LinkedIn, I'll probably be sharing some stuff about that. You can feel free to use the data. Yeah, I'll just share that again. The data is there and available right now, so you can access it right now through accessing the image. So I'll just put that in the chat. The code to produce it will take a little longer to share, just because I got to clean that up, and it's the full prediction of it. Yeah, I mean, in the short term, if there's any specific areas you're wondering, feel free to reach out. We are looking to run some more areas in Africa for certain publications, things like that.
Okay, so thank you for that. I think there are no more questions. So we can start calling off the meeting. And yeah, so thank you very much, Evans. And we do appreciate that you are kicking off our first session for this year. Our focus for this year, we were to deal much on project-based kind of sessions whereby we'll be having most of these topics, training on how to ensure that people get the best skills on how to develop solutions like now the one which we are talking about here. And those are the kind of simple prototypes which we are looking forward to build for this year. And we do appreciate it because in the event that we will call you for help, I'm sure you will be willing to give some thoughts, some ideas, and that will be very good for us. So thank you very much, Evans. For the team, for this year, our focus, as we have said, is to focus on building, on developing simple solution prototypes, which we can be able to assess our understanding. As you know that last year we focused much heavily on training and also capacity building. So we learned a lot. We also trained a lot. We had the sessions. Then this year we wanted to translate now that training knowledge and the training skills we gained into building of simple projects. And that is now what you can see learning from Evans is giving an example of now what is expected of us for this year, and we do appreciate. So our sessions are kind of well arranged, well organized in a way that you can get to see, to pick how we are moving on things. So we are trying to think about the next session. Oh, yeah. We are trying to organize for the next session, which we'll be sharing with you. You can start following up. Christopher is sharing with us our socials, our Twitter, our LinkedIn. So you can follow us through all those socials so that you can be getting an update of whatever is coming up. And for this session, for sure, to be honest, it attracted a lot of interest because so many people were interested. There is a great need to understand how carbon is affecting. Everybody is talking about carbon. Even the World Economic Forum, they had also a session about this. We have also had other discussions. So this session, this kind of topic is really, really important. It's affecting not only us in sub-Saharan Africa, but also in other regions, which means that it is something to take into high consideration. So we will share with you the notification about the next topic, the next session day, and you should expect something still building on projects because we are focusing on that. Our desire is that all the members here, at one time, one point, you will be able to share your knowledge, your expertise with another group, with somebody who hasn't ever learned about this. We build you, we grow your skill, we grow your knowledge so that you can assist yourself and you can assist others. And that is the desire which keeps us here, growing each other for the community good. We can be able to help anywhere we are, anywhere we can, because now you can see we are getting a lot of help from people from different places. Not like see here, we are late night here. Even is here is just walking up a few minutes. Yeah, and we are really helpful. So the same, you can be able to share such knowledge with other people, and we appreciate it. So Christopher shared with us all our socials. Please follow us on that. We also have our Google group. We want to share with you the link so that you can also subscribe to that for first-hand notifications. Unfortunately, we do not have any WhatsApp group, but we have the Google group, which for us works best. So I'm sharing with it. Now that is the Google group. You can subscribe there. You will be getting any notification. So Twitter, LinkedIn, and Google group. Our YouTube channel is also coming up. We will also be sharing with you once everything is ready. So thank you very much. I think we can call off the meeting and you'll be alert for the next session. Thank you very much, Evans, and we are very much grateful. Thank you.
Yeah, thanks, Nicholas. Yeah, thanks for organizing it well, and yeah, thanks for the invite.
Sure, thank you so much.
All right, take care, everyone.
Okay.
Bye, thank you.
Thank you very much, bye. We appreciate it.
Yes, thank you.